In this video, we're going to talk about using spherical coordinates. We're going to define spherical coordinates. We're going to see an example of a region described in spherical coordinates. And finally, we're going to see how to integrate a region in spherical coordinates. Consider some point x0, y0, z0 in regular old Cartesian coordinates. Well, one thing I can do is I can write the line that goes from the origin out to this point. The length of this line I'm going to call the Greek letter rho, very similar to the r we've seen back in the day with polar coordinates. That is, it's a distance from the origin out to your point. Then the next thing I want to study is an angle between this particular line, the origin out to the point, and the z-axis. So no matter where my point is, there's always going to be this projection onto the z-axis, and that the angle between the line from the origin to the point and the z-axis is going to be defined to be phi. So if you knew the rho and the phi, you could actually figure out the z value. Indeed, if I project down onto the plane, then I can figure out what the z value is, because z is just going to be the cosine of the length of rho. The z component here is just this rho cos phi. Okay, so that gives me the z component. What about the x component and the y component? Well, look at this dotted line that occurs in the xy plane. It's the projection of the line between 0 and my point down onto the xy plane. I can figure out the length of that particular line by the same triangle that I used to figure out the rho cosine. In the xy plane, this is just going to be a rho sine of phi. And then it continues a little bit like it did in polar coordinates. This rho sine of phi plays the role of the r back in polar coordinates. That is, there's an angle of theta between the x-axis, the positive x-axis, and this new projection, this dotted line, this line with length rho times sine of phi. And then if I want to figure out the x and the y components, well, there's a projection onto the x-axis and onto the y-axis of this particular line. And I can use trigonometry with respect to the theta to figure out what those are going to be. Namely, there's going to be the x component is, well, it's the length of the line, the rho cos phi, but then multiplied by cosine of theta. And then for the y component, you again take that rho sine phi, but now you multiply it by sine of theta. So I've taken my point, this x, y, and z coordinate, and I figured out how to describe the x, y, and z in terms of a rho, the length from the origin out to the point, in terms of a phi, the angle between the z-axis in this line from the origin out to the point, and an angle of theta, which is just like the polar angle theta, but you have to take the projection down onto the xy plane, and then theta plays a role similar to how it was defined for polar coordinates. Putting these three equations together, it means that if you know that rho, that phi, and that theta, you can get the x, y, and z out of it. That is, you can convert from spherical coordinates to Cartesian coordinates. Likewise, you can try solving these equations the other way around and convert backwards. All right, let's try to visualize a region in spherical coordinates. This is a portion of an ice cream cone, is how I like to call it. Okay, what's going on? The first thing I want to look at is the rho equal to 1. So the idea is anywhere along the top of this, it doesn't matter where I go, the distance from the origin all the way out to the top of this cone is exactly equal to 1. In other words, the rho is equal to 1. So that's the rho. It's part of the sphere of radius 1, but I'm going to cut out from this larger sphere. The next thing I want to think about is the phi values. What I've put up here is the z-axis, and then I put another line to one of the points on the boundary of my cone. The way phi was defined was it was this angle between the z-axis and the line from the origin out to one of our points. So what I'm basically saying here is that this phi value is constrained to be between 0 and pi divided by 6. In this particular case, I've illustrated my ice cream cone as being hollow just to make it easier to visualize, but I actually want to imagine it's a filled-in ice cream cone, so all those phi values between 0 and pi over 6 are allowed. And then if I look at the theta values were down in the xy plane. So I project this whole thing down onto the xy plane, and I get an equation of a circle, but it's not all of a circle, because my theta values were defined only between 0 and not 2 pi, 3 pi over 2. So it goes only 3/4 of the way around my circle. And that's why I have this particular restriction. It's like taking the full ice cream cone and taking 1/4 of it and throwing it out. So this is a region described in spherical coordinates. But how do I integrate functions over such regions? That is, imagine I have some function in spherical coordinates, a function of rho and phi and theta. What is the integral over some domain in spherical coordinates of this particular function? That is, I want to have a triple integral of this function with respect to a little volume. This is a three-dimensional object, so the integrand is integrated with respect to a little volume. Now, back when we were talking about polar coordinates, we put a lot of effort into studying the dA back then, and it turned out that for polar coordinates, the dA was r dr d theta. Likewise, you can do a lot of geometric arguments to discover what the dv is going to be, but I'm just going to tell them to you. It's just going to be the triple integral over the region of your function, but the dv is replaced with rho squared sine phi d rho d phi d theta. You have to really dig into the geometry to understand why that would be the case, and we're going to skip that in this video. Now that we have this formula, now that we know what to do with the dv, let's go back and try to figure out what an integral is for this particular region. Actually, what I really want to do is I really want to figure out the volume of this ice cream cone with a spherical top and this sort of cone base. So I have this triple integral, and it's a big, long mess here, and let's try to study it. The first thing is my function, which is the function 1. That is, I wanted to figure out a volume, so I'm just going to integrate in 3 dimensions the single function 1, and that's going to give me my volume. It still has these other components because the dv had these other components, the rho squared and the sine phi, and so on. Then I have 3 integrals, one for rho, one for phi, and one for theta. The rho is straightforward enough. This is cut out from a sphere of radius 1, so the rho is going from 0, the origin, all the way out to 1. For the phi value, which starts at the z-axis and leaves the z-axis by up to a value of pi divided by 6, I integrate between 0 and pi over 6. And then finally, for the theta value, as I'm going 3/4 of the way around my circle, my theta limits of integration are 0 up to the 3 pi over 2. So this is an example of how you can integrate or find the volume of a region in spherical coordinates.